How do entangled quantum qubits create spooky action? Have you ever wondered how two particles can be connected in such a way that the action of one instantly affects the other, no matter the distance? This fascinating phenomenon is known as quantum entanglement, and it involves quantum bits or qubits. Let's break it down in a way that makes sense. First, let's talk about qubits. Unlike classical bits, which can only be in one of two states, 0 or 1, qubits can exist in a superposition of both states at the same time. This means a qubit can representing 0 and 1 simultaneously until it is measured. Now, how do qubits become entangled? When two qubits interact through specific quantum operations, they can form a connection. This connection means that their quantum states are linked, and they no longer act independently. Instead, they must be described as a combined system. Once entangled, measuring one qubit will instantly determine the state of the other qubit. For example, if you measure one qubit and find it in the state of 0, the other qubit will be in a corresponding state, regardless of how far apart they are. This is where the term spooky action at a distance comes from. Albert Einstein famously used this phrase to express his discomfort with the idea that information could travel faster than light. When you measure an entangled qubit, it causes its superposition to collapse into a definite state. Because the two qubits share a joint state, the collapse of one qubit state affects the other immediately, no matter the distance separating them. However, it's important to note that while this correlation happens instantly, it does not allow for faster-than-light communication. The results of each measurement are random, so classical information still needs to be exchanged to compare outcomes. This unique connection arises because entangled qubits behave as a single quantum system. This behavior challenges our classical understanding of physics and has been confirmed through numerous experiments. These experiments include systems with stable particles like photons and electrons, as well as unstable particles such as top quarks. In the realm of quantum computing, entanglement plays a vital role. It enables qubits to perform complex computations through their correlated states, vastly increasing computational power compared to classical bits. Additionally, it is the foundation of quantum communication methods, such as quantum teleportation. In this process, quantum information can be transferred between distant qubits without moving the particles themselves, utilizing entanglement alongside classical communication. Entangled quantum qubits create spooky action by sharing a joint quantum state that links their measurement outcomes instantly across any distance. This fundamental property sets quantum information theory apart from classical physics and drives advancements in quantum technology.